Listen.
Like, do I need to say what?
I have an important question.
I may or may not have an important.
I am.
Yeah.
You just felt that hand on me.
Do you know who that is?
Yes, that is Johan.
Oh,
Right.
okay.
You're cool.
They changed like 6 people.
Right.
I think so. Same as the.
What, tonight at 10 a.m.
So if you're here, why not fill out the course evaluation saying that you're so excited for the lecture that you show up early?
Wait, Professor, I have
There is also a quiz, so go on Quirkus.
an actual question. Like, how much, I know you have like these need to know slides, right? But how much do you actually need to know for neural networks? You didn't do it.
That was also 2 hours away.
I mean,
The implementation.
like the implementation of the need to knows is extremely straightforward.
Oh,
So
are you sure? Okay.
I- very confident, yes.
So we should expect those.
One of them, yeah.
One of the implementations is need to know.
Yeah.
Okay.
Or like some kind of twist that's like not too hard, but
Sometimes, okay, I
Yeah.
see. Thank you.
yeah.
We have to get back on the way for the customer.
Okay, when you want to do MSC?
Yeah.
I'm really excited.
I want to do it after the launch.
Just do it.
Wait, that's when Charlie and Andrew are
Yeah,
saying.
train tracks are there.
I really.
When Charlie and Andrew are saying.
There's a favor diagram on that. Oh.
Other side of it.
Explode.
Yeah.
Andy, that's Andy's fault. Andy said you can explode.
Yeah. That's very well.
What? Which one?
Wait, the question I sent you, like.
There's only one answer.
It's not completely kind of.
It's all about how you interpret it.
Exciting. Highways in 76 kilometers. It's so bad. I had to come with
You go for another 500 years.
Yeah, that's what it feels like.
Don't do anything.
What?
It's so bad.
Hi, Charlie.
Don't do anything for the next.
I
I don't care.
I know. It's so hard.
did it.
It's worse than
Also, okay, I need to show you this because I think it's good, but I'm not gonna show you. Right.
Charlie, can you start hearing me?
Practice one.
Say yes.
This is. Hey, look, I can.
Already here.
Wait, hi, Charlie. I didn't do it. Oh, wait, there's.
There's activities and events.
And I knew I wasn't.
I will.
What's that looking for?
So they sent a technician to fix it, but I know where they're gonna show up. Yeah, like both he's not here. Again, assuming there is slides, which currently not sure. Oh, there's.
No, I was like.
Make it easier. I did this one right.
Wait, I like how to get this out of the work. I can definitely tell you what you're.
I can tell you.
That's a good question,
Are you
too.
ready for this?
I think good question.
I would kill. Yeah, no, I think.
I know.
I actually did it.
I don't know, I just found the current.
It was wild. Well, that works because I the equation for it. Like, we could say, oh, yeah. I don't know how to do this.
Wait, what?
You know what, my TA.
How good is the electric? Oh, there's like a.
Yeah.
I don't know, it is weird, like, there's a certain point of getting
It's about 22.
Or you come.
20, make that 22.
It was just kind of like.
This? Yeah, I know how to do this for the. Yeah, for the.
I don't think we were able to figure out the back.
Yeah, yeah, it seems like it's working. Thank you. Yeah.
Okay, great. I think that.
Bye. Oh,
Yeah, all of this, right? I did do that. I did that, I got it right after, right after you, you do like, you do the.
okay. Welcome to the survivors. I feel bad for the praxis people. I know maybe everyone's like going to praxis and not to my lectures. It's possible. All right. Do they record? They don't, right? Oh, they did. Okay. Okay. All right. Maybe they're better live. Yeah, I was on the so they have like an Anxi podcast. I was there like a couple of weeks ago, and I might have said that people should invest in index funds. I want to take it back. So anyways, so I did. So the alternative was apparently something called Paizo coin, which apparently also exists. And I kind of denigrated it as a bad investment. Again, I have not looked at the rate lately, but anyway. So okay, I do not. I have no relation to Paizo coins. Okay, so I want to kind of so today is going to be mostly kind of talking rather than writing. I'll write a little bit. I want to kind of recap what we've done with neural networks so far on at the big picture level, then sum it up, and then we'll go from there. So what were we doing kind of as a big picture kind of thing? Something like that, right? So you have a training set. So that means you have pairs of X's and Y's. And the X's are kind of the queries, the Y's are the answer. And then you have all of those different methods of saying, okay, like if I have a new X, can I map it to a Y that corresponds to it, right? And we had two possible algorithms for doing it. So we had one nearest neighbor, and the idea for, there's a quiz. If you came to lecture, why not fill out the course evaluations and say that you come to lectures? That's good. All right. So that's basically a lot of what you can do in machine learning is summarized that way. You have examples of example X's, example Y's. You have a new X, and you have some kind of algorithm for mapping the new X to something that's hopefully a correct Y, right? And we had, three different algorithms, I suppose, that we talked about. So we had one nearest neighbor, which is just that you have the new X and you compare it to every possible X in the training set. You find the X in the training set that's the most like your new X, and you output the Y that corresponds to the kind of X that you've seen before, right? We had the idea of plugging X into a neural network. So a big thing that you figure out that computes the best answers for the training set, and you just plug it in, it does a lot of algebra, it outputs something that's vaguely correct in the training set, and hopefully will be correct for X's as well. we also had the concrete example of if you're trying to fit like a polynomial to this. So if your x's and y's are just numbers, and you know that y is some kind of polynomial of x, then there is a way, like you did in the physics lab, to just make it so that the f of x that you fit is good at predicting the y's in the training set. So hopefully it would predict well on the test set as well, meaning on new data as well. Does that all make sense on kind of the big picture level? That's the big picture. Okay, so we then kind of talked about deep learning. So the idea with deep learning is you are learning a particular function of the x, right? So you're saying we have, this function. So this is how you compute the h's. This is how you compute the z's. You don't need to remember the exact formulas, although you do need to know that we're basically computing a bunch of dot product, right? And then you just say, okay, I'll try to adjust the W and the B in such a way that, again, I output the best possible thing on the training set so that hopefully when I plug in a new X, I'll compute using those formulas an output that's roughly correct. Okay. So we talked about thinking about a deep neural network, meaning where you compute a bunch of H's. So you compute, H2 using H1, and you compute H3 using H2 as a kind of customizable computer program where you don't exactly know what you're going to be computing each step, but you know that I'm going to have 8 steps in my computation. Okay. And the intuition is that kind of makes sense that it would work because it's kind of how the brain maybe works as well, in the sense that you have some neurons activating, and as a result, other neurons are activating, and so on. And it also makes sense as just if you do write a program, it usually is going to be step by step. So this is Ilya's slides, right? So we have those 2 different ideas of models of computation, meaning, ways of encoding recipes for computing y if we have an x, right? And we have powerful models. So by powerful models, we mean things that can express a wide range of computation, for example, Python. And we have what we call learnable models. So those would be, and there's no need to know here, but I'll just say it. So those would be models like neural networks, for example, where it's possible to kind of guess a little bit, to adjust the W and the B in such a way that you get a better output. With Python, hard to imagine doing that, right? So like with Python, if you start with just like a random program, you can't like adjust it bit by bit until you get the right program. People try all the time, but that's like a bad way of debugging, right? Kind of adjusting the program like bit by bit until it works. On the other hand, if the way that you compute things is just those formulas, right? Then you can just say, well, like, I'll just start with some W and B, and then I'll adjust them bit by bit. They're just numbers until I get good outputs. So that works. And the idea, sorry for flipping around, the idea is that, at the intersection of powerful models, meaning something like Python, where you can express a wide range of computations, and learnable models are deep neural networks. So they're both powerful and learnable in the sense that they can express a wide range of computations, just because there's like a lot of formulas that you can have if you get to change the W's and the B's. And it turns out that they're powerful. You can actually mathematically prove that with a big enough, deep enough neural network, in fact, it doesn't have to be deep enough. So with a big enough neural network, you can express basically any infinitely differentiable function. So, okay. So from that, so that's kind of Ilya's. So Ilya was here. He was then at OpenAI, deep learning hypothesis, and it's kind of bold, but that was 10 years ago, and I think that kind of looks more and more plausible. So the idea is that, like, human neurons, they fire about 100 times a second at most. And that kind of means that if one neuron starts to fire, then for another neuron to see the rate at which it's firing, that takes time. So essentially, if you have a sequence of like 10 layers of neurons that activate, that would be kind of equivalent to what a human can do in 0.1 second. And the hypothesis would be that anything that a human can do in 0.1 seconds, if you have a big 10-layer neural network, that's going to be possible to do as well. So what can you do in 0.1 seconds? Can't solve the ESC190 exam, most people, right? But you can like hear me talk and hopefully recognize the words that I'm saying. You can look at this and say that's a jacket, right? If you're good at Go, maybe 0.1 seconds is a bit of a stretch, but you can look at the Go board if you're good and get a vague sense of whether you're winning or losing. And kind of with Go specifically, what people find is that a lot of it works in intuition. So people don't have there are explicit ways of playing Go, of course, but kind of the really good players, they just look at the board and they get the sense of this is bad, this is good. And in fact, it turned out that neural networks can do it as well. So you can plug a Go board into a neural network and it will do, in fact, a better than human job at telling whether white or black is winning. Yes. To be honest, I know nothing about neurology. I stole this slide. So, so I know, like it's also kind of the firing. So like, even if you fire 100 times a second, so like just because you fire one time doesn't mean that you can communicate anything. Neurons do need to know like the rate at which the neighbors are firing. But to be honest, I don't do wetware. I don't know. So yeah. So all right. So, and that's kind of how object recognition with computers work, like face recognition, Go position in neural network can evaluate really well, and so on. So that doesn't account for what happens with language, right? Because images, you can imagine you take an image and you just plug it into a neural network. An image is a fixed dimensional vector, at least if you resize it to be a fixed dimensional vector, right? Language seems like it's not like that. But we've actually seen in ESC180 that you can convert words into word vectors. So that's kind of on the way of converting, a prompt that you enter into ChatGPT into something that's fixed dimensional. And in fact, kind of like an easy way of doing it that kind of works is if you have a good way of embedding words into vectors, so not what we've done in ESC180, you could just like average the vectors for all the words in the prompt, and that will work pretty okay, actually. So you do need to account for the positions, but there's like tricks to do that as well. So that kind of works. The other thing is like we don't really have like fixed inputs and outputs, or if we do, then unlike with faces, there are what's called very sparse, right? So like you can have really a lot of prompts that you could have. Like if you're asking like sensible questions, there's lots of ways of asking them. And you don't have a lot of outputs, unlike with, object recognition tasks or like Go boards where you can just like have the computer play against itself and generate lots and lots of examples of like, here's a good Go board because I'd lose if I play it out, and here's a bad one, right? So what you can do, and the insight that people had is I don't need like outputs. All I need is to learn to predict the next word. So just take all the text on the internet, and that's pretty much what OpenAI and Anthropic and all those people are doing. And then just the task is, given the first 3 words that they got from the internet, I want to predict what the 4th one is. And given the first 4 words, predict the 5th one. Given 5, predict the 6th. So that's the task. And that is what people train GPT with, right? So they take all the text from the internet that they could get their hands on. And then they just, again, make a neural network that takes, the first 1 word, the first 2 words, the first 3 words, and so on, just predict the next one. So in math, it would look kind of like this. So what you're doing is you're predicting, just like with the faces, if the correct output is V3, so the 3rd word in your dictionary. So by dictionary, I just mean like a list of all the words. Then we want the output to be like this. Right? So it's the same as with the faces. Make sense? So what shouldn't make sense is, so I kind of told you one way of doing it is you just compute the word vectors, you just average them. And based on the average of W1, W2, W3, you want to predict W4, meaning that if W4 is equal to V3, you want to output this. And then you just train. Okay? So there's kind of, you actually have, some number of words in the prompt, some number of words from the beginning of the text in which you're training. So there's going to be variable number of words. So what do you do? So in practice, you just have a context window. So you have a window in your text that's moving around, and you're saying, I'm just going to try to predict, like, starting from the 20th word up to word 2020, and then predicting the next one. And then starting from 21 up to 2021, and then predicting the next one, and so on. That's an implementation detail. There's various techniques of doing that. So what's currently happening is you're taking the context, meaning, the beginning, and you're predicting the next word. You're taking a weighted sum, not in fact the average, the weighted sum of the word vectors in your context, and you're trying to predict, based on this weighted sum, you're trying to predict the next one. A little bit more complicated than that, but basically this is what it is. So what do we need to know here? So the input, which is the word vectors that correspond to, W1 through Wn, and the output, which is, if Wn plus 1 is word number 100 in the dictionary, then the output is all zeros except 1 in position 100. Make sense? Yeah.
So word vectors, like, I guess, like, for sentences, like the word vectors dependent on the word section before it, right?
The word vector, it's like an ESC180 in the sense that the word vector is something that's fixed, right? So there's various ways of computing those. One way is to do what we did in ESC180.
So, like here when we said the correct prediction is V3, like, is that like kind of like a dot product?
Yeah, so the correct prediction is V3, means that the output that I'm looking for is like this, meaning like 0, 0, 1, where the 1 corresponds to the 3rd element in this output vector is 1. Okay, and then the input is word vectors, meaning the embeddings, right? So meaning, you have the fixed dimensional vectors like in the ESC180 that correspond to each word. So each word has like 1,000 dimensional vector of real numbers that corresponds to it.
Okay. And so like, okay.
All right. Okay. So now how do you generate responses? Well, now that you've learned to predict the next word, you enter your new prompt and you predict the next word, which is the answer, right? So sometimes you kind of adjust it a little bit. So you say like, Q colon and then the prompt and then A column. And then just say, okay, what comes after the column? What comes after that? What comes after that? And so on. Yeah.
So it's like
So people sometimes analogize it to autocomplete, right? So you can, it's not auto in the sense that you're generating it one by one. You can use it as autocomplete, right? But that's what ChatGPT does essentially, right? So you enter a prompt, and then it's just like kind of letter by kind of word by word, not quite word by word, not quite letter by letter. It's like subwords. It just generates like what's the next thing, what's the next thing, what's the next thing, and that's how the answer comes out. I mean, so the question was like, if it goes word by word, how does it understand the entire context? And like sometimes it doesn't. But essentially, the way it works, right, is you're predicting, let's say, word by word. So that means that when you're predicting W3, you already have prompt and W1 and W2, and you're saying, what's the completion for prompt W1, W2? So it knows what it said before when it's trying to predict W3. So it knows what's on the left. It does not know what's on the right because it hasn't done it yet. This is like basically true. It does look ahead a little bit, but the fact that it knows the context on the left, it doesn't know what it's going to generate in the future, and that's an issue. Yeah.
Does predicting the word, like, is it similar to how with the facial recognition, like with the weights and the dot products?
It's exactly that. Yeah. Yeah. So I mean, like usually people do it with kind of different formulas, but yes, it is that. So you're predicting the next word in the same, given kind of the previously generated stuff, in the same way that you're predicting which face it is given the image. It's exactly the same.
So given the input, like, what does that vector, like it was like 001 and then all 0, what does that represent?
So that would be what I'm targeting when I'm training, right? So when I'm training, I'm saying my inputs are all the partial texts and my outputs are the next word. So the way I operationalize it is I'm saying, if my next output word is word number 3, then I want to compute this vector as the output. And then when I'm predicting, I'll output this. And in the same way that I did with the faces, right? I just look at which number is the largest, and that would be the next word that I'm predicting. Yeah. So we're training on the large corpus of text, and then what we're trying to do during, so this is called pre-training. So what we're trying to do during pre-training is to make the network be able to predict the next word given everything to the left, right? And then when we're generating, we don't know what we want to predict, so we just say, generate. So pick the W1 such that the output, such that the coordinate is the largest when we input prompt, right? And then generate W2 such that the coordinate is the largest when we input prompt W1. And then generate W3 the same way. Make sense? Yeah. That's right. So I'm training. Yeah. So I'm training to get the weights so that the output predicts the next word in the training set as well as possible. So I think you're asking whether I specifically take into account that it's the first word. The answer is ordinarily no. So we're just saying, given everything on the left predicts the next one, and how much there is on the left, we don't really think about. Was that your question?
But like into training, there's a correct answer.
Yes.
Is it like you just your training set to the correct answer and then tell the algorithm to be like based on like these like 1,000 cases, find like the weights?
Basically, yes. So, yes. So in the input text, we know what the correct next word is, right? So if the correct next word is word number 3 in the vocabulary, we're trying for the output when we input the prompt to be as close as possible to this, right? And then when we're generating, we are outputting a similar vector. And we're saying, okay, like which coordinate is the largest? That would be my next word that I'm generating. Yeah.
You find the weights and stuff, like if you know this is the correct answer and you're kind of like you plug everything into that formula and you try to get this. So do you like put random values as weights?
So the answer is you start with random values. What you can then do is you can so like you can use calculus for that. I can tell you after. So there is a way to basically make it so that you move the weights in the correct direction so that the answers are like more correct.
Thank you.
All right. So okay. So so that's basically what it does underneath. I think you've heard about how many people heard about things step by step? Maybe not. So that's kind of the first example of prompt engineering. So I put engineering in quotes. So engineering, you might know, is a legally regulated word in Canada. If you claim to be an engineer and you actually aren't, then Engineers Canada is going to sue you sometimes. If you do that on LinkedIn, they do that. So I think it's illegal to claim to be a prompt engineer in Canada for that reason. Elsewhere, it's fine. That would be one of those trade barriers you hear about. So prompt engineering refers to basically, figuring out what prompt to use in order to get a good answer. So an early example of this is what people found is that if you ask ChatGPT or something else a question, and you say think step by step, it usually outputs a better answer. And the reason it outputs a better answer is that what it does is generate the answer word by word. So if you like force it to answer something that corresponds to think step by step, it'll output a solution where kind of there's like partial solutions along the way, which of course, as you know, helps with coming up with something that actually is true. So if you force it to do it, not force, but just say, like generate a completion where the query included things step by step, you comes up with a better answer more often. So these days, this kind of stuff is actually built into chatgpt.com. So behind the scenes, like you type in your query and it adds a custom prompt on top of your query, which includes things like things step by step. All right. But like people come up with those techniques all the time. Some of them are kind of dubious. So sometimes you hear people saying, like I experimented with ChatGPT and I found that if I tell it, I will tip you $5 if you get the answer right, then it's like more likely to answer correctly. And I don't think that's true, but some people say it. And the idea is kind of, or like maybe it's true on some models, I don't know. And the idea is kind of the same. So like what it does is it finds the most likely completion, right? And the most likely completion to things step by step would include kind of reasoning step by step, which is better than just guessing. And equally, you might think that like, on all the examples on the internet, maybe if there is like, I'll give you $5 for the correct answer as a tip, maybe the completions for that are like more likely to be correct on the internet or something. It seems kind of dubious to me. The thing step by step though is solid. That does work. So okay. So I want to spend a little bit of time kind of talking about, so this is actually a paper that I really dislike. I published like a refutation, but I think it's a good thing to argue about. And that's basically thinking about, okay, like what kind of answers could you possibly expect from ChatGPT and what kind of answers you could not expect from ChatGPT. Here's kind of, so this comes from, this is kind of Bender and Collar's octopus. So Bender and Collar are the authors that came up with roughly this thought experiment. And the thought experiment is kind of like this. So you have two people on desert islands, A and B, and they happen to be amateur astronomers, not much else to do on desert islands anyway. And they write to each other what they had observed by telegraph. And then unbeknownst to them, there is a super intelligent octopus lives in the ocean that tapped into the telegraph cable and is, the way telegraph works, right, is like every letter is encoded into like dashes and dots. And the octopus also doesn't have much to do, so it just like listens in. Okay. And the idea is kind of like that. So like one day, like A says to B, I like looked east and I saw the Big Dipper, and then I saw whatever, right? And then the question is, okay, like this octopus can't see the sky at all, doesn't know English. All it has is like, you know, dots and dashes. So would the octopus eventually be able to predict something like that if the octopus has seen like enough text, right? And the idea is that the octopus is kind of ChatGPT, right? So in the same way that ChatGPT is just like predicting it learns to predict the next thing. Well, like, can the octopus do it? And the claim in Bender and Collar is like definitely not, because the octopus knows nothing about, you know, the world that's like above the ocean. So like, how could it possibly be? So specifically ChatGPT, I haven't checked like lately. It used to be that it would just like refuse to specifically answer questions about astronomy, or specifically like, you know, like when is the next solar eclipse, stuff like that. So the question is like, in principle, is this kind of thing possible? Or because all it does, it predicts the next word, is it like in principle impossible that it could do anything like that? So that it could predict anything about the external world that's not just to do with like stupid statistical correlations. So to answer that, I kind of want to, I like this example. I know some people don't. So I want to talk a little bit about how human astronomers went around the same kind of task. Because if you think about it, you know, human astronomers, they don't live like under the ocean. However, they also for a very long time had no idea at all about physics, or if they did, the ideas were completely wrong. And what they had was observational data, right? So they looked at the sky and they wrote down what they observed. And then they wanted to predict what's next. So because like that's what they wanted to do, is like figure out what comes next, right? So the big idea that they had, so they started building models of the world, right? And the big idea that they had is that everything goes in circles around the Earth, which it definitely does not, but it's a little bit true. So if you think about the observations that you make, you can do okay. So you can, for example, imagine that the sun goes in circles around the Earth. And the period is 365 days. And you can predict where the sun is going to be, right? Something like that. And also 24 hours, of course. The problem is it doesn't predict things well, because like it's not true. In fact, like to a first approximation, what happens is the Earth goes around the sun in ellipses, in fact, and also rotates, right? What people came up with in order to better predict the observations that they had, so people sometimes say retrodict, is epicycles. How many people know about epicycles? Okay, you're like way behind. This is like 100 AD physics. Like, have a lot to learn. Anyway, so the idea was like that. Okay, like it doesn't look like actually the sun goes around the Earth in circles, but if you add those kind of epicycles, meaning like cycles within cycles, so the sun goes kind of like this, as do the stars, you get to predict better. People then added more stuff on top of it. So epicycles within epicycles. So like on top of the curly thing, as the sun goes around the Earth, you add like more cycles. And that actually predicted what people had observed actually really, really well. So Copernicus, who had a much more solid idea, actually came up with a model that was not quite as good. It was like comparable, but like not quite as good as the epicycle model in terms of predicting what you would actually observe tomorrow. It's kind of an interesting historical detail is that like Copernicus, who is, famous for bringing kind of the heliocentric model to the fore, is like sometimes is described as like being like an anti-epicycle guy. In fact, he was not. He just had a different idea about epicycles. If you read about the history of astronomy, his model is actually quite weird. He did have epicycles. There were like weird epicycles. He had strong opinions about the kind of epicycle that you need to use. So anyways, Kepler finally, and interestingly, based on just writing, right? So Kepler did not, I mean, I assume he also did observe sometimes the stars and stuff like that, but this was based on Tycho Brahe's data. Figured out that actually, like, if you do a heliocentric model with ellipses, then that actually works really well in terms of predicting the data. Right? And where, the sun is in one of the foci of the ellipse. And then there was like Newton, and Newton really had, the revolutionary idea of the law of gravity, from which you can derive Kepler's laws. Have you done Kepler's laws? No. Okay, some people have. And kind of the advantage is like Newton's framework is very simple compared to the epicycles, and it predicts very well, right? So like from Newton, you can just derive Kepler's laws that say that the Earth goes around the sun in ellipses and stuff like that. And then there was like Einstein, who observed that, who actually made like that even more accurate predictions with an arguably slightly more difficult theory. Wait, what is that? Okay, so I'm not going to delete that, but I'm not going to talk about it either. So basically, if you think about it, what do you want? What did humans do? So they figured out models that predict the training set really well. And they also tried to come up with something that's simple, that's as simple as possible. So that's a principle that's in physics sometimes called Occam's razor, which is that you want to predict correctly, and you also want a model that's as simple as possible. So as opposed to, epicycles with like 500 parameters, you just want Newton's law of gravity, which predicts better and also is much simpler. So what you could imagine the octopus doing is something like this, right? So rather than just, think about it as I'm just trying to predict the best possible, the next possible best word or the next possible best dot or dash. What you can imagine is that the octopus is saying, I want to come up with a theory of the dots and dashes on the telegraph table that's as simple as possible, right? So in addition to trying to predict well, I also want it to be simple. And in a way, that's what people did with astronomy, right? So they just observed. Eventually, you got around to doing experiments and to proving kind of the law of gravity experimentally as well. But first, people just observed. So certainly Newton just observed. So just observed like apples falling on his head and stuff, which definitely doesn't, prove anything about gravity, right? And then try to come up with a simple theory. So in the same way, what you might imagine the octopus doing is trying to come up with a very simple network that still predicts the data correctly. And you might imagine that physics works in such a way that if you do a really, really good job of finding a simple network, not like a very big network, but as simple as possible a network that still predicts, then the octopus can in fact come up with something that's like maybe not physics, but that predicts new physical phenomena. So maybe not. So those are just like ways in which you can do that if you know about neural networks. I'm not going to talk about that. So maybe with a lot of training data and the idea that the model, meaning the network, should be as simple as possible, meaning kind of to a first approximation as small as possible, maybe in fact the octopus can figure physics out, or something very much like physics, in the sense that if it hears, if it sees the kind of Morse code that corresponds to "I saw the Big Dipper," then it can predict what else you saw there. Could that work? I don't know. It hasn't been shown to work, certainly. And it's very unclear how much data you need. So it's possible that, like, in principle, it's possible if you have an infinite amount of data, but in practice, there's not nearly enough data in the world to be able to do that. But hasn't been shown to be impossible. It also kind of depends on how complex, the kind of physics you want to predict is, how complex are other things that you might like to predict are, right? So for simple things, like, for example, so in this paper, something that really gets my goat is that in this paper, this was in 2020, and one of the examples they used is, well, like, GPT cannot do arithmetic, right? So they tried to do like 2 + 2, and it said like 9 or whatever at the time, which was true at the time. And they say, well, like it knows it's supposed to be a digit, but it's not, like, it doesn't have a model for how math actually works. And that was true at the time. It's not true now with addition. So language models can in fact do addition. They cannot do division, however. Unclear kind of how much data you need. We don't know. All right. So I want to skip impossible tasks and talk kind of the other way about physical limits on computing. I have like a couple slides. So there is so we haven't done Turing machines this semester, but there is this idea. It's called the Turing thesis, Church Turing thesis, which says that basically anything that's computable is basically equivalent to Python. So if you can compute it, you can compute it with Python. That's widely accepted to be true. So are there limits to, like, physical devices that you can make just like because of physics? So can you compute stuff, or can you compute it faster? So there is kind of a question of, well, maybe you use like quantum physics in order to do computation faster. And that kind of works. So like quantum computers so far have shown that 15 is equal to 3 × 5 with high probability. So unclear whether that unclear whether there is like real speed ups to be gained by using quantum physics in order to do the computation. Of course, kind of semiconductors work because of quantum physics, but that's different because a computer that works using semiconductors, transistors built from semiconductors, you can also just build mechanically, as we saw people have done. What else can you do? Maybe you can speed up computation using physics, and that's true. You can using relativity theory, right? So if you know the twin paradox, right? So like if you send one twin into space, then when the twin comes back, they're younger, right? So you can, in fact, we've talked about complexity and stuff, but like what's the problem, right? So just like stick your computer on a starship, send it off into space, and then if the starship accelerates enough, then when it comes back, it's gonna be done, and that's great. That in fact works. It's just that, and it has been shown to work. So people, like you can send a clock into space. And when it comes back, it's going to be a little bit ahead. So the problem is it requires a lot of energy. Here's another idea of using physics to speed up computation. So this would be Zeno's computer. So the idea is kind of like that. So we had kind of constant time steps, right? But of course, if you could figure out how to speed up your time steps, you could do like the first time step would be 1 second, the second one would be half a second, and so on. And then like 1 plus a half plus 1/4 plus 1/8, and so on. That's just equal to 2. So you can do a finite amount of computation in constant time. So that's great. Again, there's like results that actually show that it works. It just requires infinite energy. So that's why it doesn't work. What about the time travel computer? So that's, by the way, a serious paper. So like there's going to be a thing. So the idea is kind of very simple. It's like the grandfather paradox computing, right? So what you do is you just like set up your computer to do the computation, and then when it's done, it just goes back in time and tells you the answer. So that speeds things up considerably. To the extent that you can do that, which is questionable. There's some theory on that. So there's kind of like fun connections between physics and computing. None of that is on the exam, sorry to say. What have we learned? I think kind of basically, and like that's how I think about the exam as well. A lot of it is just problem solving with programming. So like here's a problem, you can solve with prompt, you can solve with programming. So we've done, estimating whether a problem is feasible to solve. So that's to do with figuring out the time complexity of different algorithms. So in 190 especially, we basically spent, one way of thinking about it is we spent the time learning about C. Another way of thinking about it is we basically got to the point where we can almost implement anything implement Python in C. So that's kind of how I think about 190. We talked just a little bit about the limits of what is feasible. I did not have the time to quite do that today. And we've learned like examples of algorithms. So that is something that I always think about in 190, because at least currently, who knows what's going to be the case in 2 years. If you're interviewing for a software role for PY, what you're going to be asked about is basically data structures and algorithms. So there is no way that they can prepare you for PY interviews 2 years from now. It's just not how it works, in part because part of what the interview is trying to figure out is whether you did like work that other people have not done. So you got to practice more, and you can on leadcode.com. Again, I don't know if that's going to be popular in 2 years from now, but that is what people do now. You can practice dynamic programming there, by the way. So not very much else currently for 190, but I think you are basically ready with what you've done in 190 to go and learn similar things, just similar style, just different prompts on, for example, leadcode.com. So that's what's currently there. I don't know if in 2 years' time it's all going to be vibe coding, maybe, I don't know. I think probably not, because the reason they ask you for dynamic programming is not because actually, they need an intern to do some dynamic programming for them. That is usually not how it works. The reason is they want to see how you solve problems, and this is like a good platform to test problem solving. Yeah, so that's 190. I announced a bunch of office hours. I will also be scheduling work sessions for people to just come in and work on labs and exams. At least until Sunday, labs, projects, if you haven't done the projects from scratch, like if you work with a partner, human or otherwise, then which is not allowed, but anyway, then you want to be able to do them from scratch, essentially, even after looking at the answers. And up until Sunday, I think that that's the right strategy. Starting Monday, Tuesday, maybe kind of practicing with old exams starts making more sense. I also have a session if they're kind of really struggling with, the first couple labs, that's going to be specifically for that. That is it. This is not goodbye because I'll definitely see you in whatever it is, 9 days. But thank you very much. I'll see you around. Yeah. Bye. If you came in late, fill out the quiz. There's also course